This is Lab 1, Charged Tapes, and my name is Anjana Iyer. The purpose of this lab is to watch how the tapes interact and estimate how much charge is on a charged tape. We also want to examine the differences between viewing the tapes as a single charge or point charge as opposed to a line of charges. The system includes tape B, and the surroundings will include tape A in the universe. For U tapes, the two interacting U tapes, our expectations were that the U tapes would repel each other, and the observations matched those expectations, and they did in fact repel each other. And when rubbing a clear plastic pen on cloth or hair, the U tape negative attracted to the negatively charged pen, so the tape was deemed to be positive. In a preview of our results, the charge of the tape as a single point, experimentally and computationally, was 1.2 times 10 to the negative 8 coulombs, and then the charge of the tape as a line of charges was 9.4 times 10 to the negative 8 coulombs. The main fundamental physics principles that were used in this lab were Coulomb's law, which states that the force is equal to K, and K times Q1 Q2 all over R squared, with R being the distance between the charges, and K was 9 times 10 to the ninth, or 1 over 4 pi epsilon naught. The electric field formula could be found using F equals QE and rearranging to achieve the equation shown above. Newton's third law is also demonstrated in the sense that for every action, there's an equal and opposite reaction. This is important to understand since the tapes ripping apart are going to cause the reaction on the charges of each tape. For the experimental model, the initial conditions, the position was 0, 0, 0 meters, and the assumptions we made were each U tape has the same net charge, and we treated each tape as if all of the charge were located at a single point at the center of the tape. The length of tape B was zero point 0.2 meters, and the mass was 2 times 10 to the negative 4 kilograms. The distance between the two tapes was 0.025 meters. As shown above, the force of gravity of the tape and the electric force of the tape are opposite and equal, both being the magnitude of 2 times 10 to the negative 3 newtons. The gravitational force was found by taking the mass of the tape multiplied by the acceleration of gravity. Newton's third law was used to find the electric force. As mentioned before, it's the equal and opposite reaction. The electric charge of tape B was calculating by solving for Q, yielding 1.2 times 10 to the negative 8 coulombs. The assumptions made for the floating tape model include that the tape is a point charge and that it had evenly distributed charges, and it also neglects air resistance. For the computational model, here's the code for the lab. At the top, you can see the tape length, width, mass, and distance are noted. The atom length and electric charge are also shown. The force of gravity was calculating by multiplying g by the mass of the tape, and using Newton's third law, the electric force was the negative force of gravity, or equal to the negative force of gravity. And the charge of the tape was found using the equation shown in the code above. The other calculations included the surface area, number of atoms, number of excess electrons, and the ratio of atoms to excess electrons. And the code for the graphics were also included, and the image on the right were generated. The assumptions made, and then in conclusion, the charges were able to be calculated as if the tapes were assumed to be a single point or a point charge, and using the estimated charge, the charge can be calculated as if the tapes were assumed to be a line of charges. And then some errors that could have occurred were that the distance between the floating tapes could have been inaccurate. There could have been other factors or forces apart from gravity that influence the results. The assumptions for a single point made earlier may have introduced inaccuracies, and finite number of charges on the line of charges model as opposed to larger number of charges in real life. So what if and why? What if electrons had positive charge and protons had negative charge? What would change about the observations you made with your tapes and other charged objects? The observations would remain consistent as the tapes would continue to possess the same charge, resulting in repulsion. This pattern would also apply to other charged objects, given their reverse respective charges. The only modification that would occur in their inherent would be in their inherent characteristics, such as electric field, which would now point in the opposite direction. And why is it important to handle the charged tapes as little as possible? What happens when the charged tapes come into contact with your hands or other objects? And generally, our hands are neutral, so when the charged tapes interacts with them, it creates an attractive force. So, if anything, hands can also be positively charged, still exhibiting the same attractive force. And that is the end of my presentation, and thank you.